Let's talk about finding eigenvalues on a TI-83 or TI-84. We can use the TI-83 or TI-84 to find the eigenvalues of a square matrix. Let's do this for the matrix A equals 4, -1, 6, 2, 1, 6, 2, -1, 8. Press on. You could probably figure that one out. That's down here. Press matrix. Again, that's going to be second. And then X inverse. Notice how it's got the little blue matrix up there. That's how you access matrix. Choose the name of the matrix. So you'll come up with names. So yeah, just basically just scroll down to A and then press enter. And then you press matrix again and choose edit. So you scroll over to edit. Enter the dimensions of the matrix, in this case 3 by 3, 3 rows, 3 columns. Now enter the elements of the matrix row by row. 4 enter, -1 enter. Now be careful, use the negative sign. That's to the left of the enter. It's not the one that's just above the plus sign. That's subtraction, okay? Use the negative sign, not the subtraction sign. So 4 enter, -1 enter, 6 enter, 2 enter, etc. Now you press quit, and then y equals. Quit is, you can see where the quit button is. And then press y equals. Now you do this. You enter, wow, this looks so strange. Enter determinant. This is available under matrix and then math. Left parenthesis, you probably don't need that. That'll be automatic. A, that's under matrix and names. You got the minus sign here. This is subtraction, actually. And then X, that's under xt theta, or xt theta n. And then identity 3, that's the 3 by 3 identity matrix. So that's under matrix and then math, and then close the parenthesis. So in other words, we're trying to find the zeros of this. Recall that the way we find the zeros, the eigenvalues, is by solving determinant of A minus X times the identity equals 0. That's basically what we're entering. And then you press graph. And you'll probably get a graph that looks like this if your window is from -10 to 10. So what I would do is press window and choose a different viewing window. Since all the interesting stuff is happening, let's say for X between 0 to 10 or -5 to 10, and for Y between 0 and 60 or -10 to 60, just choose that as your window. And then you can see where the zeros of the function are. You can see that one 0 is at 2 and another 0 is at 9. So again, those are the solutions to the determinant of A minus lambda x equals, minus lambda I equals 0. And so those are going to be your eigenvalues. Now, you can't be certain that it's 2 and 9. It looks like it's 2 and 9. If you want to be more certain, you can use the 0 feature. So you press calc, that's second, and then trace. That's how we access calc. Choose 0 and press enter. And we use the arrows to go to the left of the 0. It'll ask you left bound. So you go to the left of the 0, like over here. Okay, if you want to find this 0, you go to the left of the 0. You press enter. And then it'll say right bound. So you use arrows to go to the right of the 0. And you press enter once you're to the right of the 0. And then it'll say guess. And you'll use arrows to go near the 0. And you'll press enter. And you'll find that the zeros of the function are indeed at 2 and 9. Now it's tempting to think that the characteristic polynomial is going to be lambda minus 2 times lambda minus 9, because those are the eigenvalues, but that's actually not the case. Instead, the characteristic polynomial is negative lambda minus 2 squared times lambda minus 9. Now how on earth can you look at this graph and see that it's going to be lambda minus 2 squared instead of just lambda minus 2? It's because the graph doesn't cross the x-axis. Instead, it bounces. And so if there's a bounce, that means that the 0 is going to be of even multiplicity. So this could be 2 or 4 or 6. This crosses the x-axis. This is going to be of odd multiplicity. So it could be lambda minus 9 or lambda minus 9 cubed, etc. Okay, we have a 3 by 3 matrix. If this is even, then this has to be 2. It's not going to be 4. You can't have more eigenvalues than the number of rows in the matrix. That's not going to work. So basically, your eigenvalues are 2, 2, 9. Lambda equals 2 is an eigenvalue of multiplicity 2, and lambda equals 9 is an eigenvalue of multiplicity 1.